Hi there. If you're watching this video, you're probably having a bit of trouble doing some problems that are either Atwood machines or Fletcher's trolleys, depending on how it's been taught to you and what your teacher decides to call it. Really, what you have in this question is you've got one block, and on this block, it's on a plane, and it's being pulled by a mass hanging from a string that's going over a pulley. Now, we'd like to have that pulley to be weightless and the string's massless. Physicists love things like that. So this video is probably going to take a couple of parts as we work out the question that you see here on the left of your screen. The block in the diagram has a mass of 725, so our block here is a 725 M1 grams, so that's 0.725 kilograms, and mass 2 is 0.595 kilograms. The coefficient of static friction, meaning when it's standing still, its mu is 0.47, and when it's moving, its coefficient of friction is 0.12. It's obviously less friction for a body in motion than it is for a body that's at rest. The inclined plane is 34 degrees. A wants to know what force directed directly up the incline would you have to apply to the block to make the objects start moving. To just start it moving, your F net is going to be 0, and you have to apply a force that just balances the friction and gravity and all that stuff at play. So we're clearly going to have to deal with an F net in this question. So we'll bring our picture down, and we'll see if we can get through part A in the first part of this question in the time we've got. So the data is written on the side here, and so to just start it moving, we need to consider all the forces that are acting on here. M2 is pulling this pulley downward. We'll call that FG2. Gravity is pulling in that direction. That's tending to make the pulley turn in a clockwise direction. Now, part of mass 1's gravity, but not all of it, only part of it is making this object move down. So this is FG1 parallel, meaning parallel to the plane, and this side of this vector is FG perpendicular, being perpendicular to the plane, or at 90 degrees. Now, this part of gravity right here, FG parallel, is directed down the plane. So it is trying to make it's trying to make the pulley turn in the opposite direction. So things going clockwise we'll call positive, and any forces making the pulley turn counterclockwise is negative. That way we can fix this direction stuff that we've got. So the question has this mass moving off in this direction when it's going. So the friction involved is going to be opposite to that motion, and the sliding friction is from M1, so we'll call that FF. Now the frictional force is going to be backwards or down the plane, so again it's going to be a negative number. So that being said, we can consider an F net for this system. The net or total force for this system is going to be all of the forces that are at play here on the pulley. So the forces on the pulley are, the forces that are making this pulley turn are FG2, that is pulling it. You also have FG1 parallel, this guy here is pulling it down, and you've got friction that is fighting the motion. But we have to be careful with our directions, because in our directions, some of these are positives and negatives. FG2 we said was positive because it's going down this way. FG1 parallel is making the pulley go counterclockwise, so we're going to make that a negative. So I'll quickly toss in a little negative here. And our FF is also in the same direction as FG. So we will, again, get rid of that and call this one negative. That'll be important to get our numbers right as we move through here. So I went a little bit too far there. Now we know to just start it moving, the F net is going to be 0. I'm going to plug in some of the formulas that we know. The force of gravity is mass 2 times gravity. FG parallel is going to be a bit trickier. FG parallel is sine of theta times this weight, FG1. So it's FG1 sine theta. I'll write it over here. FG1 times the sine of theta. Well, FG1 is M1G sine of theta, which is 34 degrees. This is going to go in my formula right here. m1g sine theta. Now, my frictional force, there's only one formula we use for friction. Ff is mu times the normal force. The normal force is how hard is the surface pushing on the object. The normal force would be drawn right there. That normal force is exactly balancing Fg perpendicular. Fg perpendicular, so we'll write that in. Ff is mu times Fg perpendicular. Fg perpendicular is similar to Fg parallel, except instead of sine, we write cos. So it's mu m1g cos theta. Now this seems crazy, but as you look at it slowly, it might come out at you. So mu m1g cos theta. And all of those have to add up to give 0. I'll do a quick check on my time. Okay, we get 4 minutes to continue. So we're trying to solve, in this case, what is the applied force that's going to make this 0. So we're missing one other force that we will solve for. What is an applied force? Fa. We'll put it in here. This is what we're going to solve for. So all these other terms we'll take to the other side and, of course, change their signs. So we're now dealing, we would have a m1g sine theta as a positive. We'd have mu m1g cos theta and minus m2g. That's what Fa will be equal to, and we'll find out what it's going to be. So if we start plugging the numbers in very carefully, we'll have 0.725. I'll need most of my board to get this in, times 9.81 times the sine of 34 degrees, plus our mu, which is static because we're just starting it moving. Mu static is 0.47. So you get 0.47 times m1 again, which is 0.725 kilograms. G is 9.81. Cosine of 34 degrees minus m2. I've forgotten mine like a sieve here. M2 is 0.595. So 0.595 again times 9.81. Really, I'd take a common factor out if it was me, but I'm just doing this in a straightforward manner. And we got to go plug this into our calculator. So maybe I can get that in. Bring the calculator up. Move it off to the side here. We'll do her in steps. So we turn this on. We have 0.725 times 9.81 times sine of 34. We'll write it down in steps, so that's 3.98. So 3.98 plus, back to our, so we have 0.47 times 0.725 times 9.81, and cosine of 34. Enter. That gives us 2.77. And now we take off the last one, which is, slide you this way, excuse me, so 0.595 times 9.81 gives us 5.84. It's over here, 5.84. Check our time. I'm going to calculate those in just a second, the beginning of the next video. We'll sum that up in part 2 and continue, and looks like we might even need a part 3, so stay tuned.